So we were discussing lossy source coding since the last class. And okay, before that, there seems to be some issue with people joining. I don't know why, but Google keeps turning quick access off. All right. So discussing lossy source coding in the previous class, and in this class, I'll talk about scalar quantization, which is basically the equivalent of symbol-wise compression, but now with some loss. Right. So formally, the problem setup is the following: we're given a random variable x. Think of this as perhaps a real valued random variable, maybe a Gaussian, maybe distributed according to a Gaussian. Our goal is to represent this using a finite number of bits, such that we can still reconstruct x with some distortion or some loss. Okay, so we're given x, one sample of x, which is distributed according to, which has a probability density function fx. We'll assume that the encoder and decoder both have access to the probability density function. And so we have a quantizer which takes as input a single sample and then outputs a sequence of k bits. We'll assume that k is fixed. So we're not dealing with variable length lossy compression. This will be fixed length lossy compression. And at the reconstruction, you take these k bits as input and output an x hat, which so you output some x hat, and this is going to be the reconstruction of x. So our goal is to design the quantizer and the reconstruction algorithm such that the distortion is as small as possible. So we define some distortion function, d of x comma x hat. The choice of the distortion will depend on the application, but most commonly used distortion measures are, for example, the Hamming distortion or the mean squared error distortion. So you want the average distortion to be less than or equal to some value, which we'll call delta. So this is the expected distortion that we can tolerate. And our goal, while ensuring that the distortion is less than or equal to delta, we want to make sure that k is as small as possible. Okay. So to understand this better, we will explore one particular distortion measure in as much detail as possible. So let us take the case of mean squared error quantization, which is used in many applications, including communications and image compression and so on. So the problem is that of mean squared error quantization. We're given an x, which is a real number. Okay, so it's any number between minus infinity and plus infinity, and our goal is to design a quantizer for this. So if we can represent the quantizer, or if ck is the encoded version, is the quantized version of x, then basically this means that the reconstruction can have at most 2 to the k different levels. All right. So k bits can correspond to 2 to the k possible values of x hat, right? And this corresponds to 2 to the k possible values of x hat. Right? So let's call this x1 hat, x2 hat, x3 hat, and so on, all the way up to x 2 to the k hat. All right, so these are the quantized levels, and now we need to decide. So the quantizer, in order to completely define the quantizer, we need to not only specify xi hat, we also need to specify which values of x are going to get mapped to this xi hat. right? So we could design certain thresholds, right? So let me call this alpha 1, alpha 2, alpha 3, alpha 4, and so on. So all the way up to alpha 2 to the k minus 1, right? So the quantization rule is going to be the following. If I observe a sample between minus infinity and alpha 1, if it is in this range, then the corresponding code word is going to be, say, the all zeros sequence. So k bits, k zeros, and the reconstruction is going to be x1 hat. Okay, so basically everything from minus infinity to alpha 1 is going to get mapped to x1 hat. Similarly, everything between alpha 1 and alpha 2 is going to get mapped to x2 hat. Everything from alpha 2 to alpha 3 gets mapped to x3 hat, and so on. Right? So that's the most natural form of quantizer that we can think of. So for example, if there are two levels, right? If you want to represent, if you want to a single bit quantization, now this is a problem that is there in your homework too. The goal is to design this threshold alpha and the corresponding levels alpha, sorry, x1 hat and x2 hat. Right? So if x is between minus infinity and if x is less than alpha, then q of x is going to be, say, bit 0, and if it is greater than alpha, q of x is going to be 1. So q of x is 0 if x is less than alpha, and 1 if x is greater than alpha. And what about x hat? So x hat is a function of q of x. So it is x1 hat if q of x equal to 0, or in other words, if x is less than alpha, and it is x2 hat if q of x is equal to 1, that is if x is greater than or equal to alpha. Right? This is simple one bit quantization. Okay. And the goal therefore would be to design these xi hats, the different levels, as well as the thresholds, alpha 1, alpha 2, alpha 3, and so on, in order so that the expected mean squared error is minimized. So the expected value of x minus x hat squared is as small as possible. Right? So one can view the quantization problem in two different ways. You can set up the optimization problem in two different ways. In the first case, you fix k and you want to minimize, and you design the quantizer so as to minimize the mean squared error. Or alternatively, you could fix the tolerable mean squared error or the tolerable distortion, and then based on that try to minimize k. Right? So both of them are two different optimization problems that one can solve. So in this class, we'll basically fix a particular k, and then we'll try to minimize the mean squared error, or we'll try to design an algorithm which minimizes the mean squared error. Okay. So any questions? Any questions? Okay, so let's take the simple case of 1-bit quantization. All right, so x hat is equal to x1 hat if x is less than alpha, and x2 hat if x is greater than or equal to alpha, right? So if we have fixed a for a fixed x1 hat, x2 hat, and alpha, what is the mean squared error equal to? Yes. Some x, well, that's not exactly correct. So remember, when is x?
PMF is also multiplied.
Sure, the PMF is also multiplied, but there's also something else that you need to take care of, right? So plainly speaking, this is going to be integral x minus x hat the whole square f of x dx, right? So it's integral x minus x1 hat the whole square f of x dx. But what are the limits of integration? Right, so it's minus infinity to r. So x hat is equal to x1 hat only if x is between minus infinity and alpha, right? And what is it here? x2 hat f of x dx, right? So what are the limits now? It's alpha to infinity. So for simple 1-bit quantization, it's equal to this, right? So this is the mean squared error. And in the homework, what I've asked is, I want you to, so I've given you f of x, and the goal is to design, is to solve the minimization problem by hand. So find x1 hat, x2 hat, and alpha, which minimizes this mean squared error, all right, for a specific value of f, which is uniform. So in general, if I have thresholds x1 hat, x2 hat, and so on, and quantization levels x1 hat, x2 hat, up to say xm hat, and thresholds alpha 1, alpha 2, up to alpha m minus 1, then what is the mean squared error equal to? So if x is between minus infinity and alpha 1, x hat is equal to x1 hat. If x is between alpha 1 and alpha 2, then x hat is equal to x2 hat, and so on. right? Yeah, so you'll split the integral in each interval. So the integral minus infinity to infinity x minus x hat f of x dx will be, so if I call alpha 0 to be minus infinity and alpha m to be plus infinity, this is alpha 0 to alpha 1 of x minus x1 hat f of x dx plus integral alpha 1 to alpha 2 of x minus x2 hat f of x dx and so on, right? So if I want to represent this compactly, then this is summation I going from 1 through m of integral alpha I minus 1 to alpha I of x minus xi hat f of x dx. Sorry, x minus x hat squared. Right? This is assuming that the distortion metric is the mean squared error. Right? So now for a given f of x, you can optimize this over alpha 1, alpha 2 all the way up to alpha m minus 1 and x1, x2 all the way up to xm minus 1. Right? But
Sir,
for large M, the joint optimization problem could be a bit complicated, and so we'll design a more efficient algorithm, an iterative algorithm, to minimize overall possible x hats and all possible alphas. Right. So, any questions?
sir, this x1 hat, x2 hat, these are the any values less than alpha 1, greater than alpha 1, like that, sir.
Exactly. So the choice should be such that x1 hat should be between minus infinity and alpha 1, and x2 hat would be between alpha 1 and alpha 2 and so on, right? So I mean, in principle, there's no reason to put it between minus infinity and alpha 1. It could be outside, but that will only lead to a larger mean squared error, right?
Okay, sir.
Any other questions? So in the assignment, I want you to solve this using like standard convex optimization techniques. But now I'm going to give you, for a general f of x, I'll give an iterative algorithm which lets you at least numerically obtain the best possible x hats and alphas. All right. So this is what is called the Lloyd Max algorithm, or sometimes called the Lloyd algorithm or the Lloyd Max algorithm. And the basic idea is the following. So there are two sets of parameters to minimize the mean squared error over. One is the thresholds, alpha 1, alpha 2, up to alpha m, and the other is the levels, x1 hat, x2 hat, up to xm hat, right? And instead of jointly minimizing over all of this at the same time, we'll do this iteratively. So we'll first minimize over all possible alphas, we'll keep the x hats fixed, and then minimize over alpha, and then we'll keep alpha fixed and minimize over x hat, and we'll keep doing this repeatedly. So minimize over alpha, then over x hat, then over alpha, then over x hat, and so on. So you keep doing this till the mean squared error does not decrease any further, and once it reaches a particular saturation point, you stop. All right. So 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 that is the basic principle behind the Lloyd Max algorithm, and now let's try to derive the Lloyd Max algorithm itself. Okay, so what we'll do is we'll fix the thresholds in a particular way. So for given, x1 hat, x2 hat up to xm hat, the minimizing alpha i's. So alpha I is going to be the midpoint of x1 and x2. So let's look at the picture over here. So you have x1 hat, x2 hat, x3 hat, and so on, right? So we'll fix the alpha I to be exactly in the midpoint of this. So alpha 1 will be the midpoint of x1 hat and x2 hat. Alpha 2 will be the midpoint of x2 hat and x3 hat, and so on. So alpha I is going to be x1 hat plus x2 hat divided by 2. Sorry, xi hat plus xi plus 1 hat divided by 2. Okay, and for this particular choice of alpha I, we're now going to minimize overall. So now that we have selected a particular alpha I, this can be chosen very easily. This can be computed very easily. Now we'll minimize overall possible xi hat. Okay. So to do this, so what is the mean squared error equal to? The MSC for a given choice of alpha i's and x hats. This is summation I going from 1 to m of integral alpha I minus 1 to alpha I of x minus xi hat squared f of x dx, right? So this is the mean squared error. And now let's try to minimize this over all possible xi hats. Okay, so this is MSE of, we treat this as a function of x1 hat, x2 hat up to xm hat. Okay, so this is so what can you say about this as a function of the xi hats? Is this convex? Is it concave? Or is it neither? It is convex, yes. So it's in the form x minus x hat squared. So it's quadratic in xi hat, and quadratic functions, as we know, are convex. So this is a convex in the xi hats. So that's good, which means that we can use any convex optimization tool to solve this, to minimize this over the xi hats. Right? So let's take the partial derivative of the mean squared error with respect to xi hat. Right? So each term over here depends on only one of the xi hats. So that makes life easy. So all we have is dou by dou x hat of integral alpha I minus 1 to alpha I x minus xi hat the whole squared f of x dx. Right? So if I interchange the integral and the partial derivative, then I get integral alpha I minus 1 alpha I of the partial derivative of x minus xi hat the whole square with respect to xi hat, which is 2 times x minus xi hat f of x dx. Right? So now if I set this to 0, I can split the terms into
Sir, one
yes.
minus will be there.
Sorry.
Minus of 2 into x minus x.
Sure. It doesn't make a difference. Sure. Because again, this is also xi hat minus x the whole square, right? So yeah, but anyway. Okay, so we just set this to 0, which so I can split this into two different integrals. So 2 times integral alpha I minus 1 to alpha I of x f of x dx. This would be equal to integral alpha I minus 1 to alpha I of xi hat f of x dx. There's a 2 here, right? Okay, there will be no summation because all the other terms in the summation will depend on other alpha j's, right? So for example, if I am taking the partial derivative with respect to alpha 1, then only the first term in the summation contains alpha 1. The rest of the terms contain, the first term will contain x1 hat. The other terms will contain x2 hat, x3 hat, and so on. Okay, any other questions? All right, so what is xi hat equal to? Yeah, can someone tell me what is xi hat? Yes, come on. Right, so it's the integral from alpha I minus 1 to alpha I of x f of x dx divided by integral alpha I minus 1 to alpha I of f of x dx, right? So for a given set of right, so for a given set of alphas, the minimizing xi hats are given by this. Right? So this is not very difficult to compute. If this integral, if we can compute this integral, then it means that we can compute the xi hats. Right? So we can do this. We can do this minimization iteratively. You keep repeating this in a loop till you have convergence, or you do it for a fixed number of iterations till till you don't want to anymore. All right. So any questions regarding the calculations done so far?
Sir,
Yes.
sir, I have doubt regarding this x hat. So x hat is the actually the value of q of x, right, sir?
Not exactly q of x. So q of x is going to be a sequence of bits. So let's go back to our block diagram. Right. So q of we want to represent x using a certain number of bits. This is what will be stored. Okay. So think of an image. Okay. The image is what? It is basically a sequence of intensities. It is what we see through our eyes. So you can treat it as a sequence of real numbers, right? This is going to be quantized and stored as a sequence of bits on the disk, right? That is going to be my CK. That is going to be Q of X. Now, when I say open the image using an image viewer, what I see is a reconstruction obtained from CK, right? That is going to be my X hat. So X hat is again going to be a sequence of intensities, which is going to be displayed on my screen. But the X hat is the reconstruction and not CK. So Q of X is CK, but the reconstruction is X hat.
Fine, sir. But some mapping is there from Q of X only, right, sir? X
Correct,
hat.
correct. So basically you can treat this whole thing as a single block, call it, I don't know, G of X, and G of X is basically X hat.
Okay, sir.
So again, we typically we take alpha to be the midpoint. This is in reference to Kusuma Priya's question. So the alphas. So you first in each loop, you first minimize over alpha, and then you minimize over x. So right, x hat. Right, cool. Right. So you first minimize over alpha, then minimize over x hat. So when you minimize over x hat, the alphas may not be in the midpoint anymore, may not be the midpoint of the xi hats anymore. Right. So in each loop, first minimize over alpha, then minimize over x hat. Not the other way around. Right. So you're not exactly minimizing over alpha, you're choosing a specific alpha. Right? You're updating alpha. So in fact, if you think about it, suppose that I have only 2 points. Okay, suppose that I have x1 hat and x2 hat, right? If this is my alpha, then under what conditions do you think the midpoint would be the one which minimizes the mean squared error?
X1 hat plus X2 hat divided by 2.
Yes, but is that always optimal?
When the distribution is uniform.
Yes, uniform.
Sure, when the distribution is uniform, or slightly more generally, yeah, exactly. So Sheikh has pointed it out. So it's when the distribution is sort of symmetric about the midpoint, right? If it is not symmetric over the midpoint, then the optimizing alpha would be not exactly in between x1 hat and x2 hat. Right? And regarding Anuradha's question, the x hats are known to the decompressor. So you choose fx, right? So given an fx, you first design the quantizer and the decompressor. So you design x hat and alpha, and these are given to both the quantizer and the decompressor. Right? The decompressor does not really need to know alpha, because it's only the compressor which has to know alpha. That is going to be the one which is going to do quantization. The decompressor only needs to know what the x hats are.
Sure, why are we using an update rule for alphas but not for xi's? Like, can't you also minimize over alphas using some technique?
You could, potentially you could, but this is kind of simpler, right? I mean, of course, certainly if you want to minimize the number of iterations that you need to perform, then you should also minimize over the alphas, right? But this, as it turns out, is good enough.
Okay, thank you.
All right, so let's see an example of what you've seen so far. Let's do an example problem for the Lloyd-Max algorithm. All right, so I've just written up some code for designing the Lloyd-Max quantizer for an arbitrary random variable which is bounded between some particular value. So it's a random variable which is bounded between -10 and 10. Okay. So we won't solve this exactly. So all of this will be solved using numerical techniques. So after all, since I'm trying to, I can't do integration by hand. I'm just going to approximate an integral by a summation, and delta x is going to be the step size. But anyway, that is not particularly important. I can change the number of levels, right? So I'm going to try to construct a 2-bit quantizer. So 2 bits corresponds to 4 levels. All right, and let's choose some particular distribution. Let's say that this is Gaussian. Okay, so f of x is e to the minus x square by 10. Okay, so what is the variance of this Gaussian? Right, so the variance is 5. Okay, so let's see. So this is what the distribution would look like. This is not exactly a Gaussian because I'm sort of truncating it to lie between -10 and 10. But anyway, it's close to being a Gaussian. All right, so this is the PDF. And now I'm going to design the quantizer for this particular PDF. So I start with an arbitrary, so I just initialize x hat and the alphas. Uh, According to any rule, you could just choose this randomly. So I'll start with x hat to be -6, -3, 3, and 6. Okay, these are going to be my initial x hat. So x1 hat is -6, x2 hat is -3, x3 hat is 3, and x4 hat is 6. Okay, and my thresholds are going to be, so this is alpha 0, which is instead of -infinity, I'm just taking it to be -10. So alpha 1 is -4. So this has to lie between -6 and -3. Okay, and then I have, right, and then I have 0, which lies between -3 and 3, and 4, which lies between 3 and 6, and 10, which is the equivalent of +infinity. All right, so these are going to be my thresholds. So the quantizer is going, okay, so anyway, so the number of, and I'm going to run it for a certain number of iterations. Let me run max. All right, so I'm going to run this for a certain number of iterations. In each iteration, I'll do the following. I'll first set the alpha i's to be in the midpoint of x hat and x hat, my xi hat and xi hat -1, xi -1 hat, sorry. right? So thresholds of, so alpha j is x hat j plus x hat j minus 1 divided by 2. I'm just rounding it off to 3 bits, but that's not particularly important. The mean squared error, and then I'm going to minimize over x hat. Okay, so the x hat is basically, it's the integration of x f of x and divided by integral f of x between alpha I minus 1 and alpha I. Okay, and at each iteration I'm also calculating the mean squared error. Okay, so that is what I'm going to do. And if I run it for, let us say I run it for just one iteration. So if I run it for one iteration, this is the quantizer that I get. So the xi hats are something close to -5. The second point is something like -2 and 2 and 5. All right, these are xi hats, and the thresholds are going to be this and this and this. So as long as x lies in this particular interval, it's going to get mapped to this particular point. If it lies in this interval, it gets mapped to this particular point. If it lies in this interval, then it gets mapped to this particular point. Okay, and note that in this particular example, the the alpha I is not really the midpoint of two levels, right? And the quantizer as a mapping, yeah, again this should be g of x, is basically looks something like this. So as long as x lies in this particular interval, it is going to get represented as this particular value. If it lies in this interval, it gets represented as this particular value. If it lies in this interval, it gets represented as this particular value. So the quantizer is basically just a step function. All right. So this is for one iteration, and the mean squared error in the first iteration turns out to be whatever 1.04. Now let's run it for two iterations. Yeah, so I run it for two iterations. In the first iteration, it's 1.049, but in the second iteration, I see that the mean squared error has gone down. It's only 0.705, and now the quantizer looks different, right? So the quantization levels are these four dots on the x-axis, and the thresholds are basically these. Right, so these are going to be my thresholds. Okay, so, and this is what my quantizer is going to look like. So if x lies in the range -10 to whatever this is, -2.7 or something, it's going to get mapped to -4. If x lies between -2.7 and 0, it gets mapped to whatever -1.2. If it lies between 0 and 2.7, it gets mapped to 1.2. And then if it lies between 2.7 and 10, it gets mapped to +4. So this is after two iterations. Now, if I run it for, let's say, 5 iterations, I see first iteration, the MSE is 1.04. After two iterations, it's 0.707. After the third iteration, it is 0.595. But then after that, it remains constant. Right? So just 3 iterations is enough for it to converge. Right? And this is what the quantizer will look like. All right. So let's do this for maybe some other density. Let's pick a weird looking density, say let's say it's minus x square x whole square by 10. Right, so the distribution has two modes. Maybe let's make this 4. Right, so this is a density which has two peaks. Okay, so now let's see what the quantizer looks like. After one iteration, this is what it looks like. So the MSE is 1.432, but it looks like it doesn't change at all. So even just a single iteration is enough, and it converges pretty fast. So although you in principle you may have to run the quantizer, you may have to run the algorithm for many iterations, it usually converges very fast. And so if this is the PDF, then it just converges in like 2 iterations. Repeat. The point of trying to change the xi hat. So these are not changing the levels, right? You're trying to design the xi hats. So this is even before seeing x, right? The goal is to choose the best possible xi hat and the best possible alpha. And all we are doing is just iterative optimization. We're just trying to solve an optimization problem over here, right? Yes, so this is being designed before. So it's, think of it like the Huffman coding problem, right? You first get px, right? Given the px, you're trying to design the code words, and that is basically what you're doing here. You're first designing the code words, and this is shared with the compressor and the decompressor, and then they're going to use that to quantize and reconstruct, to compress and to decompress. Right? So here, so at in each iteration, I'm choosing the alpha i's to be the midpoint, right? So I first choose alpha I to be the midpoint, and then I'm going to choose, and then I'm going to minimize over x hat. So initially, it doesn't matter how you choose the alpha i's, how you choose the x hats, because you're anyway going to run the optimization algorithm. Any other questions? Any other questions? Okay, so this was about scalar quantization. And that is the equivalent of symbol-wise compression. Right? But as we've seen in the case of lossless compression, it is far more optimal to choose to do blockwise compression instead of symbol-wise compression. The price that you have to pay is, of course, an increase in the encoding and the decoding complexity, and of course in the design complexity of the code. But if you want to really minimize the compression rate, you should do blockwise encoding and not symbol-wise encoding. And that is also true in lossy compression, and blockwise lossy compression is also what is called vector quantization. All right. Okay. So I'm just pausing it here. So Anuradha asked a question. What about MSc? Sorry, in reference to what is this question? Right. So for a given k, the MSc achieved using block or vector quantization will always be lower than that achieved using scalar quantization. So if you want to really achieve a low mean squared error, then you should be doing blockwise coding or vector quantization and not scalar quantization. Scalar quantization, the advantage of scalar quantization or symbol-wise encoding is that the design of the quantizer becomes easier. It's easy to choose the thresholds and the levels. And it's also easy to quantize because after all, you're just implementing a simple step function. But as we'll see, optimal vector quantization for in high dimensions is in fact challenging. It's not easy to design or implement a vector quantizer. Okay. So let's think about the problem of vector quantization. So in scalar quantization, we're given a real number, and our goal is to sort of partition the real line into a number of non-overlapping intervals, right? So you partition it into non-overlapping intervals, and each interval, if x lies in that particular interval, then that interval is represented using some reconstruction point. So this is a representative for that particular interval. All right, and the idea, the geometric idea behind vector quantization is basically the same thing. Right? So you're given a vector in Rn, right? Let's say R2. So maybe X is Gaussian distributed over R2, right? And now the goal is to choose a set of reconstruction points. So a bunch of points in R2 and these decision regions. So these black dots correspond to the different levels that we had earlier. So these are what we'll call reconstruction points. Or representatives. So these were the levels that we had earlier. And then we also need to choose the thresholds. So now the thresholds aren't going to be threshold for X and threshold for Y, but basically our goal is to somehow partition this into different regions, non-overlapping regions. Right? And so if X lies in this particular region, it's going to be represented by this reconstruction point. If X lies in this particular region, X lies anywhere in this particular region, then X lies in this particular X hat is equal to this particular point, right? So these are going to be my X1 hat, X2 hat, X3 hat, and so on. All right. So of course, all of this is if X is a real valued random variable, and typically if you're dealing with mean squared error quantization. Okay. Now, more generally speaking, the goal is to, we have xn. So xn comes from some joint distribution fxn, typically IID f of x. Our goal is to once again represent it using 2 to the k levels or k bits, and to reconstruct it, you get xn hat such that the distortion, the expected xn hat is less than or equal to some n delta, right? Or the per symbol distortion, the per symbol expected distortion is at most delta. And given this constraint, our goal is to minimize the rate. So the rate is simply k over n, and we want this as to be as small as possible. All right. Any questions? Okay, so we'll officially end the class for today. If you have any questions, then I can answer them now.
Sure.
Yes.
So here, like vector quantization means almost it is like increasing step size only, right?
So it is not step size, right? Instead of dealing with intervals, we're now dealing with regions, correct?
Okay, sir. Fine. Okay.
So if you think of it in terms of, so scalar quantization corresponds to whatever a step function, right? This is your g of x, and whereas this is your x, right? So vector quantization, for example, 2D vector quantization, you can think of it in terms of a well, not even a three-dimensional graph. It has to be in 4 dimensions. So really the right picture to look at is this. All right. So if x lies in one particular region, then that particular point is the representative.
Okay, sir. Algorithmically, how do we write this region, sir? How do we obtain?
So that is really the difficulty of vector quantization over scalar quantization. Even describing the region is not very easy, right? So one way to describe each region would be the following. Given a set of reconstruction points, x1 hat, x2 hat, and so on, the region let's call it let's call it AI corresponding to xi hat. So one way to describe the region, a sort of natural way of describing the region, is to consider this as the set of all points which are closest to xi. So if you look at the distance from x to xi hat, then this is less than or equal to the distance to any other point, xj hat, right? So that is how we chose the alphas in the one-dimensional case, right? So the midpoint, we chose the sort of intuition behind choosing the midpoint as the threshold between x1 and x2 was that all the points to the left of the threshold are closer to x1 than to x2, and all the points to the right are closer to x2 than to x1. Right? And similarly, we can choose the regions for each xi in this particular fashion. And this is, in practice, this is what people start off doing. Right? So if you don't know, if you don't have too much information, then the best possible choice would be this. If you want to minimize the mean squared error. Right? And this is called the Voronoi region corresponding to xi hat.
Okay, sir. Thank you.
Right? But then even computing the Voronoi region is not easy. So that is what makes vector quantization a lot more challenging than scalar quantization.
Okay, sir.
So Ritvik asked a question: for arithmetic coding, can we consider any arbitrary ordering? So please choose A to be less than B to be less than C. So you can map A to 0, B to 1, and C to 2.
Sir, in last question, mean square error is required to be found using program. So you
Correct.
use the formula statistical mean
Correct.
square formula.
So yes.
So
So there are two
which is
things.
to be
One
used.
is you're given a bunch of points, right? Let's call them x1. Let's use a different notation. So x of 1, x of 2, up to whatever, I think it was 1000 points, right? Right. So when designing the algorithm, you assume that x is random and then choose the level and the thresholds so as to minimize expectation of x minus x hat squared. But what I want you to report is the following: 1 by 1000 of summation I going from 1 through 1000 of x of I minus x hat of I, the whole square. So this is the empirical MSE that you get through observations, and this is what I want you to report. Right?
Sir, in question
Yes.
it is written q of x instead of x hat.
Okay, fine. So this is, yeah. So this is what I want you to report.
Okay, sir. Then my question is, if x hat, for example, x hat is a q of x, and
Okay.
we are having the input array like you
Okay.
have provided. So how do we compare? Means they will have a different unit. I mean, one is on the x-axis, and if we compare, if we draw simply two level quantizer, so it is on the y-axis q of x. So how do we are calculating? Like you are saying here that it is a reconstruction after
Yes.
q. Then it will be
Correct.
fine, sir. X of hat.
Yeah.
And if
So
it
that
is
is what I'm
Q,
expecting. So yeah, I guess my notation was not correct in that particular problem.
say in the whole question, you use this Q of X, and even we are comparing with respect to Q of X only.
I don't remember what the question exactly stated, but basically this is what. Okay, so maybe there I used a different notation, right? I didn't introduce the notion of bits in that particular question, but basically I was referring to Q of X as X hat.
So if in this particular problem, like
Yes.
in the starting of class, if we
Yes.
consider this Q X hat is equals to Q of X, then it won't be the case, sir. Like
Yes,
X1
so that's
hat.
what I'm saying. The notation that I used in this particular class, I apologize for the confusion, but the notation that I used in the assignment was different from the notation that I used over here. Right? So this whole thing was Q in the assignment,
Okay, sir. Now I got it.
right? Yeah, in hindsight, I should have used a different notation either here or over there. I should have maybe called this G, or maybe I should have called this F, right? So you have an encoder and you have a decoder, but in the assignment, within the assignment, the notation is consistent. So in the assignment, Q of X is basically X hat.
Okay, sir.
Okay. Okay. So if we write a program for question 1, can we submit it in Google Classroom and directly write the answer on paper? Yes, that's fine. You should fill in the form anyway. Your final answer should be filled in the form, and then you can give your solution on paper, or you don't have to show all the steps on paper if you're writing a program. But then if you're trying to work everything out, then I expect you to write it on paper.
And sir, in the second question, if we make a program for parsing, then it will be fine, sir.
That's also fine.
Okay,
But
sir.
sure, fine, that's fine.
And sir, in the first question, the encoding start from 0 point something. So, means
So I want you to write it as, I don't want you to include the point. So it
yes,
should
sir.
be just be a
One
binary
hash.
sequence.
Yeah, as you mentioned, one hat and this binary sequence after 0
Yes.
point, right,
So
sir?
so if it is, if your arithmetic code word is 01010, then just enter quote 01010. That's it.
Okay, sir.
Sure.
Yes.
Sure. Lossy compression is generally used for images and video, but not text, right?
Sorry, could you repeat the last couple of words? I didn't hear it clearly.
Lossy compression is just used for images and videos, but not text data,
Yeah,
right?
true.
So how about if we use lossy compression on text data, but then use like what happens if we use lossy compression on text data is we may get incorrect spellings of sorts of the words.
Correct.
How about we use a spell checker at the decompressing end after we do a lossy decompression if we use lossy compression?
Well, you could, but then how do you correct the spellings? So then you need some other algorithm in order to correct the spellings, right?
Yes, sir. Like every device already has a spell checker, right?
True. But then effectively, so okay, so what you're proposing is the following. You take text and then you apply lossy compression, and ultimately you get some text with errors, and then run something like a spell check in order to get back the original text. Is that?
Yes, sir.
but effectively, if you look at this whole thing as a single block, what is your ultimate goal? Your ultimate goal is still to get the original text exactly, correct?
Yes.
And if that is your goal, then ultimately the minimum rate of compression that you can do over here will still be the entropy. You can't go any below entropy if your goal is to ultimately use a spell checker and get back the original text. Right? Because effectively end to end, this still needs to be a lossy compression scheme. Sorry, lossless compression scheme.
Okay.
Correct?
Yes, sir, but
Uh-huh.
spell check in essence is giving us more information of sorts, right?
Correct.
So
Correct.
include
So
that also in the entropy part.
no, so the thing is, I mean, you need to be so that is so if you are using an optimal compression algorithm, optimal lossless compression algorithm, then it is taking care of that additional redundancy of the spellings and everything else, right? So this scheme can never get you below the best possible, theoretically best possible compression scheme for English text.
Okay.
Right,
Uh,
but
no, sir.
certainly your idea is correct. I mean, this is one particular compressor which wherein you use an off-the-shelf lossy compressor and then try to spell check and correct it later. Correct, that's a perfectly valid point. uh, but but then if you're trying to compress it at a rate even below entropy, then for large enough texts, the spell check will not be able to correct all the errors. There will be errors which cannot simply cannot be corrected.
Okay. Okay. Yeah. All of them may not be corrected, but
Exactly.
we may decrease the loss, but not the okay. Okay. Yeah.
Yes. Yes. Yes.
But sir, while we are calculating the entropy, in
Mhm.
this case,
Mhm.
spell check is giving us another random variable y, which when combined with the x, h of x comma y can be like lesser because we already know y of sorts, right? So do we include the spell check's random variable when we are calculating the entropy, or do we not?
No, not really, because ultimately it's the entropy of the text, right? And
Okay,
this is there is a lot of dependency. There is long range dependency in the text, but that is in, so everything is within the text itself.
okay, thank you.
Okay, so if there are no further questions, then
Sir,
yes, yes, Ashok.
sir, we want to change our the paper we have to record and submit. Can we do that?
Sorry.
Uh, we have to submit a paper, a recording of a paper presentation
Correct,
on
correct,
28th, right?
correct.
So right now we have chosen a paper that is a bit too much for us. Like we have
Okay,
it has too much notation. Like it went too deep into graphs, mark graphs, and equivalence of those things and stuff.
okay,
And we want to change that paper, and we are looking into some paper which is in the same domain, like which is in graph compression itself, but a little
uh-huh.
less